Hi, and welcome to the Blast Radius Containment demo with Cisco Secure Workload. Every security team talks about perimeter defense, but the question that keeps practitioners awake is not whether someone can get in, it is what happens after they do. Today, I'm going to show you how Cisco Secure Workload answers that question. A compromised workload sitting inside your network has the same east-west access as every other workload. It can reach your database, it can probe your message queue, it can move laterally to anything it can see. The perimeter did not stop it, because the breach already happened. What stops it is segmentation, and specifically enforcement at the workload level. Let's take a look at our environment. I have two Ubuntu workloads. Demo app represents an application tier. Think of it as a workload an attacker would land on first. DemoDB represents a sensitive database tier. This is the blast radius target. Both machines have open sockets on ports 5432, 8080, 6379, and 3306. This will simulate a realistic attack surface. There's also my management computer that I had to include for the demo purposes. I will allow it to SSH toward the two VMs. The agents are already installed for this demo. Now let's take a look at the automation in place. Everything in this demo is driven by Python scripts talking directly to the Cisco Secure Workload API. No manual configuration in the UI. This matters because it means everything you see could run inside a CI/CD pipeline. You could tag a workload, create a scope, enforce a policy as part of your deployment process before the application ever goes to production. Let's begin the demo. The first thing we do is give the workloads an identity. We upload a label, application equals demobrd, to both VMs through the inventory tags API. Cisco Secure Workload then uses that label to define a scope. The scope is not an IP range, it's a query. Give me everything where application equals demobrd. That means if a workload moves or its IP changes, the policy will follow the label, not the address. Now let's create the workspace to write our policies. We will have three explicit rules. The application tier can reach the database on TCP 5432. This is the one legitimate path. My management console can SSH to both workloads also. Everything else will be denied. No exceptions. The catch-all deny is not a default. It's an explicit statement. If it's not on the list, it will not happen. What you're observing is the creation of inventory filters that will help me create my policy in an easier way. The automation behind the scene has created the entire workspace and has created also the policies. I have also invoked the policy analysis that has triggered analyzing the policy behind the scene. And as you can see, at this point in time, enforcement is still disabled. Now, before we go on enforcement, let us see what the word looks like. I'm running a traffic simulator from two perspectives simultaneously. You will see my Mac probing both VMs on every port, as well as Demo app probing DemoDB on all ports. This is going to simulate our lateral movement later on. Everything is open. All ports respond except port 80, which seems to be closed on the VMs, and we're going to go from this state to a more restrictive state in the next iteration. Now it's time to push our enforcement. The policy we defined moves from analysis to enforcement. Cisco Secure Workload is going to push the policies on the native firewalls of each of the VMs that we have in this demo. And as you can see, the enforcement now is active on the UI. Now let's run the traffic simulation again. From my Mac, you will see that SSH survives. Port 5432 is blocked, even from my own machine, because the policy only permits the application workload to reach the database, not my laptop. From Demo app, only port 5432 to DemoDB is allowed. Every other lateral movement path is gone. The blast radius has been reduced to a single line. And this did not happen at a firewall somewhere upstream. It happened at the operating system on the workload itself. You can check the enforced policies by looking up the concrete policies on the workload's identity card. You can also connect to the VM directly and check the NFTable rule set. Back on the UI, you can go and check all the traffic that has been permitted, rejected, or that seems to be escaping one of the policies. What we're observing here is all the tests that we have made where we have the consumer and provider showing up, as well as the provider port that has been probed. You can narrow down your search to the consumer and provider you are looking for. In that example, I'm looking for my 2 VMs. This will directly take me to the corresponding machines. And I could look for a specific traffic. Here, for example, the rejected traffic. Let's narrow down the searches to my machine and see what are the results from that consumer address. Let's select one. You can use the quick policy analysis to check the verdict on a specific direction. We can look at the analyze policy. This is the candidate policy if your policy has not been yet enforced, and also the verdict on the enforced policy. Since our analyze policy and enforced policy are the same, the verdict will be the same. Let's take another example. Let's look at this permitted traffic and do a quick policy analysis from my machine towards one of the workloads on port 22. As expected, the policy decision is allow since this traffic is allowed. Let's summarize what happened. We defined workload identity through labels. We wrote a policy based on our intent to reduce a workload's attack surface. We enforced it through an API call, and the enforcement landed on the native firewall of the operating systems of every workload in scope. This use case can be extrapolated in many ways, such as defining your zero trust-based policies on your applications to the strict minimum and essential for an application to work, or create an incident response management framework and automate everything through Secure Workload. And in case of a breach, you can automatically react. Thank you for watching.